And the crazy part is, Netflix uses a different model serving architecture for recommendations, depending on whether you're browsing on your TV versus your phone.
Wait, really? Different architectures for the same recommendation engine just based on the device? That sounds complicated. Why would they do that?
Exactly. That's what we're diving into today, model serving architectures. Because choosing the right one isn't just about picking the fanciest tech, it's about understanding your specific needs and constraints. And believe me, getting this wrong can be painful.
Painful how? I mean, a slow recommendation is annoying, but is it really a disaster?
Think bigger. Imagine Uber's surge pricing models failing because the serving architecture can't handle the real-time demand spikes. Suddenly, no drivers, angry customers, and millions in lost revenue. Or a fraud detection model at Stripe that's too slow to prevent fraudulent transactions, costing them and their users serious money. The cost of a poorly chosen architecture can be catastrophic.
Okay, I'm convinced. High stakes. So let's break it down. What are the main options we're talking about here?
We've got three main contenders: online inference, batch prediction, and streaming. Each has its own strengths and weaknesses, and the best choice really depends on the use case. Let's start with online inference.
Online inference. That's the one that comes to mind first, I think. Real time, right?
Exactly. Think of it like this. A customer adds an item to their Amazon shopping cart, and immediately the system generates personalized recommendations based on that action. That's online inference in action. A request comes in, the model processes it, and a prediction is returned in real time.
So low latency is the key advantage?
Absolutely. It's ideal for scenarios where immediate feedback is crucial, like fraud detection, personalized recommendations, or real-time pricing. But here's the thing. It can be resource-intensive. You need a robust infrastructure to handle the constant stream of requests with minimal latency.
Resource-intensive meaning expensive?
Exactly. You're paying for that responsiveness with higher compute costs. Think about needing GPUs running constantly, even if traffic is low at certain times. And scaling can be tricky. You need to be able to quickly spin up more resources to handle peak loads.
Okay, that makes sense. So what's the alternative if you don't need that immediate response?
That's where batch prediction comes in. Instead of processing requests one at a time, you group them together and run them through the model in batches.
Like overnight?
Exactly. Think of generating personalized email recommendations for millions of users. You don't need those recommendations instantly. You can run a batch prediction job overnight, process all the user data, and then send out the emails in the morning.
So the advantage is cost savings?
Big time. You can utilize cheaper compute resources like spot instances, and you don't need to maintain a constantly running high-performance infrastructure. It's much more efficient for large-scale, less time-sensitive tasks.
But what about the downside, besides the obvious latency?
The biggest downside is stale data. Your predictions are only as good as the data you use to generate them. If user behavior changes significantly between batch prediction runs, your recommendations might be irrelevant.
So if someone buys a tent and camping gear on Monday, they might still get ads for baby clothes on Tuesday if the batch job hasn't run yet?
Precisely. And that can be a frustrating experience for the user. Think of it like this. Batch prediction is like cooking a huge stew. Efficient for feeding a crowd, but not ideal if someone wants a specific dish right now.
Okay, online is instant, batch is scheduled. What about streaming? Where does that fit in?
Streaming is the hybrid approach. It's designed for scenarios where you need near real-time predictions, but you also need to process data from a continuous stream of events.
So it's not quite instant, but faster than batch.
Exactly. Think of detecting anomalies in network traffic. You're constantly receiving data from various sources, and you need to identify suspicious patterns as quickly as possible. Streaming allows you to process that data in small chunks, constantly updating your predictions.
So what kind of technologies are we talking about for streaming model serving?
You're looking at things like Apache Kafka for handling the data stream, and frameworks like Apache Flink or Spark Streaming for processing the data and running the model.
And what's the trade-off here? There's always a trade-off.
Complexity. Streaming architectures are significantly more complex to set up and maintain than either online or batch prediction. You need to manage the data stream, ensure fault tolerance, and handle data transformations in real time. It's like building a constantly flowing river. You need to carefully manage the flow and prevent any blockages.
Okay, so online is fast but expensive, batch is cheap but slow, and streaming is somewhere in the middle but complex. Is that a fair summary?
A very fair summary, but here's where it gets interesting. Most engineers assume that real-time always wins. They default to online inference because it sounds the most cutting edge. But that's often a mistake,
Why? Doesn't everyone want the fastest possible predictions?
because speed isn't always the most important factor. Think about model retraining. If you're constantly retraining your model with new data, the latency of your predictions might not be as important as the accuracy of your model.
So you're saying it's better to have a slightly slower but more accurate prediction?
Exactly. And that's where batch prediction can actually be better than online inference. You can retrain your model on a large dataset overnight and then use that model for batch predictions the next day. This ensures that your predictions are always based on the latest data, even if they're not delivered in real time.
Okay, that's counterintuitive. So how do you actually choose the right architecture? What are the practical steps?
Here's what I recommend. First, define your latency requirements. How quickly do you really need the predictions? Don't just assume you need real time. Quantify it. Is sub-second latency critical, or is a few minutes acceptable?
Okay, latency is step one. What's next?
Second, estimate your cost tolerance. How much are you willing to spend on your model serving infrastructure? Be realistic about your budget and factor in the cost of compute, storage, and maintenance. Remember, the cheapest option isn't always the best, but the most expensive option isn't always necessary.
And finally,
Finally, consider your data pipeline. How frequently do you need to retrain your model? How complex is your data transformation process? A complex data pipeline might make streaming a more attractive option, even if it's more complex overall. Think of it like this. Choose the architecture that fits your data, not the other way around.
so latency, cost, and data. Got it.
And remember, don't be afraid to experiment. Try different architectures and measure their performance. A/B test different approaches to see which one delivers the best results.
So don't just pick one and hope for the best, actually test it out.
Exactly. And remember, the best architecture is the one that solves your specific problem, not the one that's the most hyped.
All right, this has been super helpful. I feel much more equipped to navigate the world of model serving now.
Model serving is all about finding the sweet spot between speed, cost, and complexity. Nail that, and you'll be architecting models that not only predict the future, but also deliver real business value.